So let's find out what the capacitance is now that it's filled up with air. And it looks like it's 519 picofarads. So 519 picofarads. So again, notice filled with air and it's much higher because it's thinner, okay? The D is smaller. And so to get the dielectric constant, you know, we have to make sure that the only thing we change is we fill up the space with paper. We don't change the thickness or the overlap area. So that's why we needed to make a measurement with the paper spacers. And we'll just say the spacers didn't take up much space. It was mostly air. Okay, so now I can put the paper here. And that'll give me the same thickness, and hopefully I got the same overlap, and I get a capacitance of 1,253. 1,253 picofarads. So the dielectric constant of paper then would be this 1,253 over the 519. And notice, of course, it's the same unit, so the dielectric constant is just a number. There are no units that go with the dielectric constant. And so we can learn something about our material this way. How much does it reduce the field? And so paper reduces it, looks like a little bit more than 2 here, about a 2.4. Where this is 3, well, not quite 4, so 3 and change, 3.5-ish, somewhere in there. But I'll let you do the numbers there. But like I said, I really like this step 2. I like all the steps. 7's a little long for what value you get, but you do hopefully see it's proportional. But 8 is really good. And then finally, I know, long lab. Hopefully you did take a break earlier. One more thing to do, and probably the easiest part of this, but really nice to see. There's nothing for you to write down. It's just to, again, like all the steps, try to get you to understand the capacitor a little bit better. And so the capacitor stores charge. And so that stored charge could be like a battery in the sense that once you store it, you can then use it to run a light bulb. And that's what you're asked to do in number 9. So number 9 says take a capacitor, a big capacitor, none of this pico or micro stuff. And so we've got this capacitor. It's really big, and I don't mean physically big. This really isn't physically very big, although you know, this is physically about the same size as probably these. But there's an important difference. These metal plates are rolled up really tight that if I unrolled it, it probably would have an area about the size of our campus. It's a huge area and they're really close together. And so this one, when it's rolled up, doesn't have much area. It's maybe about the size of one of these tabletops. So this one is 1,000,000 times more capacitance than this one. This is 1 microfarad. This is 1 farad. It's got 1,000,000 times more capacitance, but it does that 2 ways. Number 1, it has more area, but number 2, it's closer together, which is also why this says, do not charge this more than, what does it say? 5.5 volts. Okay. Now it gives a little bit of safety, because sometimes I do charge it up to 6, but I'll be a little careful and go 5.5. But the plates are so close together that the electric field can get so strong that you actually tear the dielectric apart. That's the dielectric strength. Now we're not dealing with dielectric strength in the lab, but you saw that in the lecture. And so there's always a limit on these capacitors. And so this one has a maximum of 5.5, whereas this one, this spacing is really far apart, which is why you don't get much capacitance. But it says, go ahead, you could put up to 630 volts on this gun. So that's a lot more voltages. And so that's the main difference between them one. So I got to be careful when I say bigger. I don't mean physically bigger, because that one physically is bigger. And the spacing between the plates is physically bigger on that one. But this one is bigger in its capacitance. So this is 1 farad. So what I'm going to do is take this capacitor, I'll put it in front of you, I'll grab a couple of wires, maybe I'll just take it off this meter since I think we're done with everything else. And I'm going to take my power supply and I'm going to turn it on. And I think I was playing with it and adjusted it to 6 volts earlier, yeah. Let me cut that down just to be a little bit on the safe side and follow their recommendation. Do not go more than 5.5. Okay, so there's 5.5. And so let me then actually hook it up to my power supply. So I'll take my 2 wires. And first time you're seeing the power supply here in this course. But, oh no, we saw it last week when we hooked it up to make our equipotentials. And so this is the plus and this is the minus. And so what would happen as soon as I hook this up, you might even see this number come on. Next chapter we'll start calling that current. That is actually registering really how many electrons are flowing out. So right now we're filling it up. And this is going to take a little while. That was the advantage of using this big capacitor, is what happened now is a bunch of negatives come on here and started filling up, I'll call it the right plate, and it would chasing electrons off and bringing them in here off the left plate. So it's taken a little while, but I think we finally have gotten to the point where our capacitor is what we would call fully charged. Okay? Although it says it's putting a little more on, and so that last stuff's going to take a while. I won't wait the whole time frame for it to get all the way up there. Looks like it's dropping down here. But it has essentially got a lot of charge on here. And the point here now is to kind of give you, the student, a feel for the capacitor. Because like I said, capacitors are neat. They do a lot of things. And the most basic and easy for students to understand here at the beginning is that stored charge can then be used to run something. Maybe, in this case, a light bulb. And that's what I'm going to do. I'm going to grab this light bulb and hook it up. And you're going to watch it run. Maybe a really good example of this is there's one just like this inside your computer. And I'm thinking desktop computer, not laptop. Because if there should be a momentarily break in the power, a half a second or something, the computer could still run on the charge that is in the capacitor for that half a second. And so maybe you're working at your computer, maybe this has happened to you before, and all of a sudden the lights kind of flash and go, oh. They didn't go off permanently, they just flashed. And so you saw the lights go off for a half a second and then come back on because the power diminished. But your computer was fine. Your computer was like, okay, power's off, now I'll just run on this capacitor. And so that capacitor is always there as a backup, as storage. Now it has its limits. It only has so much charge, so it can only run your computer for a half a second. If the power actually goes off for a second or two, you'll see the whole computer go down and just go, you could buy bigger interrupt emergency backup stuff that says, okay, this could run my computer for 3 seconds or 4 seconds or 5 seconds. Some of them could be 15 minutes. Now, usually get that much, they're more than capacitors. They go to batteries. Our capacitors have not yet gotten to be that strong yet. But there's a great career, what they call the ultimate capacitors. Just get rid of batteries altogether and start charging up capacitors. There'd be something so much better. But at this point in our technology, we could not do that. We could not put a capacitor, say, in our phone and have our phone work all day. We could put a capacitor in our phone and make it work for about 7 seconds. But nobody's going to want a phone that has to be recharged every 7 seconds. So you'd rather just have a battery for that. So our batteries have really grown. And so it's kind of a constant battle. Are our batteries going to get so strong that they will now run our technology that we need? Or will our capacitors get so good that we won't even need batteries? But I think the capacitors are still a long way off. Well, I'm chit-chatting away here. Let me show you this last one. So here it is. I'm going to disconnect it. And so I claim right now that there is charge on here, and it's just sitting there. I haven't done anything with that charge. it wants to run something. And so when I hook it up, it will run the light bulb. Yay! And so there you see the light bulb on. And so if I read this last step, you were to write down how long does the light bulb last. It says here in step 9, to get a feel for the behavior of the capacitor in a circuit with a battery, go ahead and hook up, and it says 6 volt with a 1 farad capacitor. How long does it take for the current to stop? Now I know we really haven't gotten to current and resistance yet. That's coming up. That's the start of next chapter. As I told you, with these 3 chapters, we're going to do a bunch of practical devices. Looks like we're at about 30 seconds, by the way, right about now. I don't know if I started it quite on time. Maybe I should let you guys look at the timestamp, because I kind of lost track on the clock there when I went over. And I guess I would say it's probably off. Technically, I don't know if you can really see. I can see a faint amount of glow, so it's technically on. But it's so small now that I really couldn't do anything. So at this point, it would be like, you know, having a flashlight with weak batteries. It's like, yeah, it's on, but it's not doing its job. It's time to recycle those batteries and get new batteries. Now I can't even see it, so I think it's off. So now it's officially off. Maybe that was as much as 60 seconds. But I'll have you look at the timestamp on the video, and that's what you're to write down. But that was to give you a feel for the capacitors. So not much to do in that last step. Anyways, hope all that was good. It was very, very long, but it's really a good lab, and I talked a lot purposely with hopefully really getting you in the best way I can what these capacitors are, how they're built, how you can affect and change them by their distance, their area, the dielectric constant between them, what happens when you hook them in series and parallel, or a combination of series and parallel. That's really the feel for what we're trying to get out of this electronics. And that's where we're headed with electronics. In fact, some of you aren't even in the electronics course, and so this stuff about current and resistance, you're probably experts at that by now. But for most of you, this is all new, and this is where we get started. What is a capacitor? What is charge? Going into next week, we'll then get into things like current and resistance. All right, well, I better call it quits here and call that good for now. Bye.